Lord. There we go. Well, I've been looking forward to today for a long time because we're talking about the world of carbohydrates, and it's going to be really sweet. No? Thank you. Thank you. That is the appropriate response. Groans. We're going to learn some basic things about structure, and then we're going to go kind of crazy talking about all the different things that carbohydrates play a role in. We'll talk about diabetes and HA1C. We'll talk about the Maillard reaction, which is how the lovely golden brown color that you're supposed to bake things to, and how that generates molecules that are colorful and flavorful. We'll learn why, for example, if you want to make pretzels, you use lye or a basic solution. And then we'll talk about lactose intolerance. We'll also talk about blood typing and various carbohydrates that are found all over in biology. And we'll just scratch the surface today, and then on your problem set, you'll have a chance to consider even more and different kinds of carbohydrates. So they're called carbohydrates because their molecular formula is generally, at least for the basic compound, CN and then H2O, also N. So they're a carbon with water. And there are three basic carbohydrate structures that you need to know. And they exist in both open chain and cyclic hemiacetal forms. So, for example, and then among the cyclic hemiacetal forms, there are a couple of different options. So the first is D-glucose. In the cyclic hemiacetal form, it looks like this. Excuse me, we'll number the atoms of the glucose ring like this: 1, 2, 3, 4, 5, and then this one, the one that's outside the ring, exocyclic, is 6. We'll call that a hydroxymethyl group. And then this one on carbon 2 is a dash. This one on carbon 3 is a wedge. On carbon 4, it's a dash. On carbon 1, there are two options. One is for the OH on carbon 1 to be a dash, and this is the alpha anomer of glucose. Anomer is another way of saying epimer or diastereomer. And it differs from the other option of glucose in the configuration of that C1 stereocenter. So all the other stereocenters in glucose have the exact same configuration of each other, but the difference between the alpha and the beta anomers is the configuration of the C1 stereocenter. Okay? So these cyclic hemiacetal forms are called pyranoses. Pyran means a six-membered ring containing an oxygen. So, for example, if someone writes alpha D glucopyranose, they're talking about this molecule here. And if they write beta D glucopyranose, they're talking about the diastereomer on the right. It turns out, Couple of issues of nomenclature with carbohydrates. The D portion of the glucose name refers to basically this stereocenter. There was a way of talking about stereocenters and chirality before the R and S rules. This was L and D, L for levo and D for dextro, left and right, respectively, like chirality, left hand and right hand. Some of that has persisted, but for our purposes, the identity D will refer to the stereochemistry of carbon 5, the last stereocenter in glucose. Of course, carbon 6, is that a stereocenter? No. Okay. So if we look at that, so the last stereocenter in glucose, carbon 5, when we draw glucose this way and it's a wedge, that's D stereochemistry. If we want to be a little bit more precise, which maybe is a good idea, if we assigned R and S configuration at that stereocenter, for a proton would be the priority 4 group, oxygen would be the priority 1 group. This carbon, C4, is bonded to an oxygen, 2 carbons, and a hydrogen, whereas this carbon, C6, is bonded to an oxygen, 1 carbon, and 2 hydrogens. As we go down the list, we get a tie until we get to a carbon versus hydrogen comparison. This becomes C2, this becomes the priority group 2, this becomes priority group 3, 1 to 2, 2 to 3, 3 back to 1, that is clockwise rotation, and the priority 4 group is down. So that means the stereocenter is what? R. Good. That is the pirate's favorite stereochemical configuration. Yeah, okay, good, good. Good, you're getting it, right? If you want to throw objects at the front of the classroom when I do stuff like that, feel free. Yeah, so DR configuration at C5 means it's a D sugar, all right? Now, D and L don't always correlate with R and S. It just happened, and there is a story behind how D and L originally came to be. We're not going to worry about it. Most carbohydrates will have the D configuration. In other words, the R configuration at C5. Now, how do you determine whether something's an alpha anomer or a beta anomer? Something is alpha when the C5 group, the group coming off of C5, is on opposite side of the ring as the group coming off at C1. Just as we used the terms cis and trans to describe whether groups are on the same side as of a double bond as each other or opposite sides, so we can use the cis or trans language to describe groups that are on the same or opposite sides of the ring. So the C1 hydroxyl is trans to the C5 hydroxymethyl group. That was a weird way of writing it, hydroxymethyl group. And so when that's true, when the C1 hydroxyl is trans to the C5 hydroxymethyl group, that's what it means to have the alpha configuration. If the C1 hydroxyl group is cis to the C5 hydroxymethyl group, then it's beta configuration. All right, that'll be important later on. Yeah, go ahead.
Can the other alcohol groups be switched and that would still be the same, or will it always be like?
Great question, yeah. If the other alcohol groups on C2, C2, C3, and C4, those, the configuration of those stereocenters is going to be reflected in the name glucose. So if you see gluco in the name of a sugar, that tells you what the configuration of C2, C3, and C4 should be. So the D part tells you what the configuration of C5 is. The A, alpha, or beta tells you what the configuration of C1 is relative to C5. Is it cis or trans? Yeah.
Which forms have like the axial hydroxyl group? Which forms?
Yeah, let's talk about that. Which forms have axial versus equatorial? Let me show you how to take a carbohydrate like this and draw it in its chair form. It's most convenient to start with a chair like this with oxygen in the upper right-hand corner. If you do it any other way, that's okay. You can still get the right answer, but you'll have to play around with it a little bit. Then, starting with I'm noticing that this oxygen here in this overhead view of the ring is this one. I'm going to go around the ring clockwise, starting with C1, 2, 3, 4, and then 5. And then I'll just go stereocenter by stereocenter. From the overhead view, C1 is a dash. What's the down position on C1? Is it axial or equatorial? Yeah, axial. So the overhead view above comes from looking down on this ring from the top of the page. What about this group at C2, which is a which is a dash? What's the down position on carbon 2? Equatorial, right? And then on carbon 3, that's a wedge, so that means up. What's the up position on carbon 3? Also equatorial. C4 is a dash, down, equatorial, and then C5, the hydroxymethyl group, is up, and at this carbon that's also equatorial, and we can draw it like this. So in alpha D glucopyranose, and this is why glucose is the easiest one to start with, if you draw it in its chair form, C2, 3, 4, and 5 are all equatorial. Yeah?
Wait, could you re-explain real quick what equatorial is? That should be a straight line, not a dash or a wedge.
No. So in a six-membered ring, we talked about how six-membered rings aren't perfectly flat. They pucker a little bit. That is, carbons 1, 3, and 5 come up out of the plane of the page, and carbons 2, 4, and 6 poke down into the plane of the page to give you this sort of chair zigzag shaped structure. And on each carbon in the chair, recall that one substituent, one CH, will be axial and the other will be equatorial. In this chair, carbons 1, 3, and 5 are all, from our overhead view up here, carbons 1, 3, and 5 are all poking up out of the plane of the page. And if we look at it from the side, it looks like that. And then carbons 2, 4, and 6 are poking down into the plane of the page. And if we look at it from the side, it looks like that. At carbons that are poking up out of the plane of the page, I call those up carbons. The up CHs are up axial. Axial means they're pointing either from this point of view, they'd be pointing straight up at you. From this point of view, they're pointing straight up to the top of the page. Carbons 2, 4, and 6 that are down carbons, their up positions are not axial. Instead, they are equatorial. Equatorial means they're pointing up, but they're still splayed out along the edge of the ring. So if you imagine a sphere, here is the axis of the sphere and here is the equator. Axials point either to the North Pole or the South Pole. Equatorials are either angled up or down a little bit, but mostly straight out. Yep. Okay, on the down carbons 2, 4, and 6, the down substituents are axial, pointing straight downward. And then on up carbons 1, 3, and 5, the down groups are down equatorial. So to draw something in its chair, you look at the overhead view, you choose a starting point for the oxygen, and then you say, okay, at this position, oxygen was here, carbon 1 is here, this OH is down, and the only down position I have there is axial. Similarly here on carbon 2, the OH is down because it's a dash. The only down position I have on carbon 2 is this down equatorial position. The up position would be occupied by a hydrogen, and it's axial. Yep. Okay, other questions? So then, if I drew the beta anomer, the beta D-glucopyranose, C2, C3, C4, and C5 would be exactly the same, but at C1, the OH group would be up. So it's probably easiest to memorize beta D-glucopyranose, then remember alpha, I need to switch the configuration at C1, and then on from there. Other questions? Okay. This carbohydrate has an open chain form. And we'll talk about how to interchange between the two. I'll show you the open chain form in almost the same orientation as we're showing the cyclic hemiacetal. C2, C3, C4, and C5 are going to be exactly the same in the open chain form as they were in the cyclic hemiacetal form. But C1 is going to be an aldehyde. And so glucose is an example of something that's called an aldose. It is a carbohydrate that is an aldehyde. And if you'll forgive me, I'm going to change the color of our anomeric carbons here to be just a little bit more convenient for when I talk about things. All right. So how do you get the closed chain form of glucose from the open chain form? It turns out you've already seen this in our mechanism, one of our mechanisms that we did last week. Glucose is an aldehyde, therefore you would expect glucose to be a level 1 electrophile, and you'd expect it to be attacked by a nucleophile. And it just so happens that the C5 hydroxyl can get very close to the aldehyde. And so what happens is likely the following. A base, could be an enzyme, could be water, removes a proton from the C5 hydroxyl, which attacks then the C1 aldehyde, attacks the pi star, breaking the carbon-oxygen pi bond, and at the same time, likely some acid, probably water, protonates the oxygen as the pi bond is breaking. That's one of the ways you could push the arrows. If you don't like that, if you prefer the following alternative, that's okay too. You could show base removing the proton, electrons kicking down here onto the oxygen, lone pair attacking the pi star, breaking the pi bond, lone pairs on the oxygen, attacking, getting protonated by an acid. Either of those options is fine. The one I showed you first requires fewer arrows, so whatever you want to do there. That closes the ring and gives you this cyclic hemiacetal structure. What is a cyclic hemiacetal? Well, a hemiacetal in general is an aldehyde where an OR group has attacked the aldehyde and the tetrahedral intermediate got protonated. In other words, it's this deprotonation, addition, and then protonation steps all in one to get to this hemiacetal. And you can recognize the hemiacetal carbon because it will have an OH and an OR attached to the same carbon. Okay, questions about all of that? Yeah.
How would you do the open chain for the different views if that's not, like,
Oh, so you want the open, the sort of sideways view of the open chain form, or do you want to just lay it out linearly? Sorry, what are you asking? Like, are you wanting the? Do you want me to draw it like that?
no, for the ones that are,
Oh, you want
side
to look at it from the side view? Okay, sure. If we drew the open chain form from the side as though it were the chair, this is what it would look like. And again, if you wanted to draw the mechanism from that direction, you'd just do this. One thing to remember is that depending on whether this aldehyde oxygen is pointing upward or downward when the ring closure happens, that will determine whether you get the alpha or the beta versions of glucose, the alpha or the beta diastereomers of glucose. What I've just barely drawn for you is how you get the alpha version, and what I've drawn for you here is how you get the beta version. And it turns out that the alpha and the beta versions of glucose, or anomers of glucose, are in equilibrium with each other through the open chain form. So if you put glucose in water, you're going to immediately get a mixture of the alpha and the beta anomers. And one way to communicate that you have a mixture of the alpha and beta anomers is as follows. You can draw either the chair or the overhead form of glucose, but at the anomeric carbon, you put a squiggly line like this, and you angle it in between the equatorial and axial positions. That communicates I have both in solution. That does not communicate that the OH is actually angled out at that ridiculous angle. It has to be either equatorial or axial, but it does communicate that I have a mixture of alpha and beta anomers. All right. Other basic questions about glucose? Go ahead.
There was one in the comments that was linear, and then it shows it turned into like real.
Uh-huh.
Can you go over that one?
So one that's linear and turns into a ring?
There's no question now.
Or just the linear form, yeah.
Right, and that was a question you didn't have to do, right? Because we didn't get there.
Yeah, I was just.
Let's have a look. Okay, so show how the cyclic form is converted to their open chain forms in water. Is that right? Is that what you're asking? Okay. What I've shown you here is how the open chain form is converted into the cyclic form. What we'll do then is the backward step. What if you started with this? How would you get the open chain form? Sorry, conversion of cyclic to open chain. All right, so let's just start with, say, let's choose the beta anomer. I know in the problem set it's a squiggly line, I'm just picking one of them. When you see glucose in its cyclic hemiacetal form and you want to go to the open chain form, start first by identifying the hemiacetal carbon. That's the carbon that's bonded to an OR group here and an OH group here. When you see that, remember that the OH group in the hemiacetal will become the carbonyl oxygen in the open chain form. And remember that the OR group is basically going to be the leaving group. Here's a hydrogen there, and the hydrogen and the adjacent carbon C2 are just spectators. So in order to form the open chain form, we will, with a base, remove these protons, remove the proton on the pink OH group. Electrons will kick down to do an elimination reaction, and they will kick off the OR group, which will pick up a proton on its way out. And that will give us that open chain form. In the open chain form, what used to be the hemiacetal carbon is now the carbonyl carbon. What used to be the OH group is now the carbonyl oxygen. And what used to be the OR group has left as an OH group. Okay, questions about that? The other part of that question was a related sugar. This is not the same as glucose because you've got a 5-membered ring. It turns out that this carbohydrate also has 6 carbons. And if you compare to how we've drawn glucose previously, you will see that C4, C5, and C3 have the exact same configuration in this carbohydrate that, that glucose does, with a major difference. And that is that the hemiacetal carbon in this sugar is at C2 instead of C1. This is called D-fructose. And we'll encounter it later, though you've certainly heard about it if you've ever heard about high fructose corn syrup. All right? So let's just think through this. Here's the OH group on hemiacetal carbon 2. Here are 2 spectator groups, C1 and C3. They're carbons, they're not leaving groups. And then here is the OR group. All right? So once you've drawn that, using what we just did above, draw a mechanism using a base and an acid as needed to convert the closed chain form of fructose into an open chain form. Take a couple minutes and do that. How you doing? Need more time? What do you think my first step should be? Deprotonation, good, of, yep, so remove the proton from the hemiacetal OH group. Electrons kick down to form a pi bond between the oxygen and the blue carbon. Then who leaves? Green oxygen leaves. And as it's leaving, it will pick up a proton from some acidic group. Could be water, could be an enzyme depending on the situation. Then drawing the open chain form, we just keep everything else in the exact same place. Here's C1, here's C2, here's C3. What should I have on, what should be the functional group on C2? Yeah, isn't that interesting that the open chain form of fructose is a ketone, not an aldehyde? Fructose is an example of what we will call a ketose. And the reason it is, instead of, whereas glucose is an aldose, the reason it is because the open chain form of glucose is an aldehyde, whereas the open chain form of fructose is a ketone. Yeah?
So, one of the questions on the problem set was that we didn't get to was circle the hemiacetal group.
Yeah.
So that would be the green, the purple OH, if you're looking at the left side, the
Yeah.
purple OH, the blue carbon, and the green oxygen.
Yes, I mean the hemiacetal group is the OR, the OH, and the purple carbon. Yeah. And notice that the hemiacetal carbon in an open chain form is either a ketone or an aldehyde. And you can tell whether it's going to be a ketone or aldehyde even without drawing the open chain form by looking at what these gray things are, the non-oxygen things attached to the hemiacetal carbon. If one's a hydrogen and one's a carbon, it's going to be an aldehyde. If they're both carbons, it'll be a ketone. Question, yeah?
So for the alkane from 1 to 2 on the open chain form, because it's trigonal planar, we get rid of the dashes. Is that what
That's right. So on C1 in the open chain form, it used to be attached to 4 things. Now it's only attached to 3 with the pi bond. It's sp2 hybridized, so we can lose the dashes and the wedges. Yep. All right, others? All right, so here's a good time actually to go ahead.
I just want to reiterate, if the hemiacetal carbon is bonded to a hydrogen, it would be an aldose.
Yeah, if the hemiacetal carbon is bonded to at least to one hydrogen, one R group and one hydrogen, it's an aldose because in the open chain form it's an aldehyde.
And if instead it's an oxygen, then it's ketose.
If it's 2 carbons, it's a ketose.
Okay.
Yeah, notice the difference between C1 up here and C1 here. Both are attached to the OR and the OH. Yeah, the only difference is in 2 carbons versus a carbon and a hydrogen. All right, so now's a decent time to talk about why having high blood sugar is bad for you. You've learned that aldehydes and ketones are at what level of reactivity for electrophiles? Level 1, that means pretty reactive, pretty subject to nucleophilic attack. It turns out that your proteins have lots of nucleophiles in them. Among the most nucleophilic are amino groups. So here is an example of an amino group in a protein side chain. This one happens to be called lysine. But right now, all you need to worry about is the fact that here is an electrophilic, or here is a nucleophilic nitrogen. And glucose is an electrophile, and you've just demonstrated that that's the case by having us draw the open chain form. So what can happen is a reaction called imine formation. We did this before, and we went through the mechanism, but it was kind of complicated. You saw this previously in the reaction of 11-cis retinal plus the protein opsin to make the protein rhodopsin, in which 11-cis retinal is attached to rhodopsin via an imine linkage. And you can see the mechanism in detail on the mechanism handout that I provided. Look up the key and I will show you. It's basically, and you saw it before, but basically the nitrogen attacks the carbonyl carbon, and you eventually get a product after a few steps, a few proton transfers, and some leaving group leaving. You eventually get a product that looks like this. And again, if you need a refresher on that particular mechanism, it's in the mechanism handout. And this process is called glycation. You may have heard about that. The functional group we just made is called an imine. You can recognize an imine because it will have what used to be the carbonyl carbon doubly bonded to a nitrogen. That carbonyl carbon will still be sp2 hybridized, but the double bond is now to a nitrogen, not an oxygen. In this process, we lose water as a leaving group. And again, you can see the mechanism for that in the mechanism handout if you want to. Some people call imines Schiff bases, named after somebody whose last name I guess was Schiff. I don't know. I don't particularly call them that. I like the word imine. But glycation can interfere with protein function. If that lysine was supposed to do something as a nucleophile, and then you glycate it to form an imine, suddenly that lysine is no longer available to do what it's supposed to do. In addition, there are a ton of downstream reactions and rearrangements that this imine can do that generate other electrophiles that can react with other things. Glycation eventually leads to something that, if you want to know more about, you could look up. It's a fascinating field and it's pretty complicated. It's called advanced glycation end products, some of which can have damaging effects biologically. So when you make imines with glucose on some of your proteins, you can damage their function. Damaged proteins don't do their appropriate job, and then you can get some of the symptoms of diseases. You can also get some disease symptoms from the advanced glycation end products associated with diabetes. So poor circulation, poor kidney function, problems in the eyes, problems with neuropathy, and so on. And it's all because the aldehyde of glucose is a level 1 reactive molecule. Now, if you go to question 2 on your quiz, this has you try to deal with a question that you may have already encountered in your life if your physician has ever ordered labs. Oops, that's the answer, not the, I didn't want to show you the answer. Oh well. There we go. Nope, still the answer. What happened? Ah, okay. Fair enough. So if you've ever had labs where they asked you to come fasting and they wanted to measure your glucose, your fasting glucose level, and your triglycerides and so on, in addition to measuring glucose blood level, there is a test that measures something called HA1C. And the reason that, well, we'll talk about why people do this in just a second. HA1C refers to something called glycated hemoglobin, meaning hemoglobin that gets modified on one of its amino groups with glucose. And they think mostly it's this amino group that's at the very end of the hemoglobin. This is the free amino group at the N terminus of the hemoglobin protein. Here's the aldehyde. Based on what we just talked about, I want you to draw the imine that forms when the amino nucleophile attacks the aldehyde electrophile, carbonyl carbon. Okay, go ahead and get started on that. Take just a minute and a half. Okay, if you want, compare notes to with a friend or seatmate or acquaintance or nemesis. If you have a nemesis in the class, feel free to compare your answer with them. Who am I kidding? I am your nemesis. Okay, anybody feeling lucky or confident or both? Anybody take the Felix Felicis potion? What is that? Is that from Harry Potter? Pronounce it incorrectly. That's all right. Yes. I'm not as much of a Potter nerd as I am a Star Wars nerd. May the Force be with you. Star Wars trivia is extra credit on the test. I could be talking to that. I probably could. But you're probably better off studying this stuff than Star Wars lore. Yeah, that's a trick question. What he really said was no.
Dude, I think you would so good. I'll take some.
Takes you a lot harder.
My extra credit Star Wars question would be something like, what happened to Heavy the Clone Trooper?
He got
Clone Trooper,
shot.
the animated
Got
series.
blown up.
He sacrificed himself to notify the Republic that the Separatists were about to attack, and they were passing a base on what planet? Rishi. Somebody knew that? No? Yes. Minor knows it. So now Miner's going to do a Star Wars extra credit review session. Star Wars lore.
Just something like that.
Okay. Do you know? Can you Can you draw the, you're absolutely right. That is the first step. You're actually overachieving just a bit because I didn't ask for the mechanism, but do you know how the imine final product looks?
Well, the water would come off.
Okay, so yeah, see if you can just draw, go a little bit further and draw what would happen after the water comes off.
With our group, can I just do our group?
R groups is totally fine. R is for I don't want to redraw the molecule.
It would be. And then R again.
Okay, and you're missing a pi bond between the nitrogen and the carbon.
Yeah.
Good, good, thank you. Yeah, so the way that, let's give him a hand. The way you're envisioning this happening is right. Lone pair electrons, we need to deprotonate the amine. Then lone pair electrons need to attack the carbonyl carbon. We need to break the pi bond, and the OH needs to get protonated. And this is the correct intermediate that you would get from that process. If you wanted the OH group to leave, what you would do is have these electrons kick down to form a pi bond. Then OH would leave as it's picking up a proton from the acid. And that would get you not quite to this imine, but it would get you close. So yeah, this is what happens when your blood glucose level is high enough that hemoglobin starts to form an imine. And just to recall, the imine functional group is the carbonyl carbon. Water left is the oxygen of the aldehyde ends up leaving as water, and then the nitrogen of your nucleophile ends up in place of that carbonyl oxygen. So that's glycated hemoglobin. Now let me just ask you this, you may or may not know this. Why do they want to know about glycated hemoglobin? Why not just measure your blood glucose concentration and be done with it? It's not necessarily dangerous, but it provides complementary information. Anybody know what the average lifetime of a red blood cell is? I don't actually know, but I think it's like 30, 60 days maybe? Oh, somebody knows. What is it? 120 days? Okay, sweet. So a red blood cell that gets loaded up with hemoglobin is going to be circulating in your blood for 120 days. Therefore, whereas a glucose concentration in your blood tells you what it is today, HbA1c tells you how much your hemoglobin has gotten glycated over the past 120 days on average, which is a longer term measure for how your glucose level regulation is. It's possible to be really, really well regulated today because you know you're going in to get labs today, so you're really well behaved, but every other day you were not taking care of things. And so HbA1c allows your physician and people looking at your results to be able to say, your glucose level, even though it's great today, has not been very well regulated over the past 60 to 120 days. So that's what they're looking for, imines. Okay. Another interesting story on imines. When we cook, most recipes, so let's see, quiz time, chocolate chip cookie recipe. What are the ingredients? Butter. You need about a stick of butter, you need an egg, cup of brown sugar, cup of regular sugar, cup of flour. Maybe a little bit of salt. You test it on this. Yeah, a little bit of baking soda / powder, and then you need the chocolate chips, right? Okay. So, and then you mix them up, you put them in, make the little chocolate chip cookie spheres, which you eat a few of those, unless your mom told you that you should not eat them because they have eggs and you could get salmonella. But then you roll your eyes and said nobody's ever died from eating cookie dough, which may or may not be true. I don't know. We can look that up. People are like, if I die from eating cookie dough, it will be because I have eaten too much and then die of a heart attack. It probably will not be because of salmonella. Now watch, tomorrow someone will be here to say that Dr. Price died of salmonella after eating cookie dough.
Someone in 2009.
Someone in 2009 died, okay. Alright, so it is an issue. Okay. So you put it in the oven, you bake it 350, 375 until what? Till they're golden brown. What does the golden brown color come from? There is a reaction which we'll talk about later today called caramelization, which involves sugar browning, but that occurs at higher temperatures than this. So what's happening is that you have amino groups in the protein that's in the eggs and the flour, and then you have a ton of glucose. Now we're talking a little bit about what table sugar is. It's not glucose, but it has glucose in it. And that can, whatever that table sugar is, can equilibrate and release glucose, which can form its open chain aldehyde form. The aldehydes form imines with the nitrogens in your proteins, just like we drew here. And then remember how I said there are some downstream reactions that can generate other molecules, some of which are colorful. In biology, we call them advanced glycation products. In cooking, we call that the Maillard reaction, and they generate colorfully brown molecules called melanoidins. And that's what all baked goods, the crust on bread that's nice and brown, or cookies, these are because of imine formation from the aldehydes of glucose with the amines that are on your proteins. The reaction actually happens faster in the presence of a base. In the mechanism that you drew, you had a base removing a proton from the nitrogen in order for the nitrogen to be able to attack as a good nucleophile. If you use a basic solution like sodium, like baking soda, you can get the reaction to happen faster and you can get things more colorful. So for example, if you want to turn, let's see, do we have any former Little Caesars employees in here? My sons used to be Little Caesars, one of my sons used to be a Little Caesars employee. The pretzel crust, you wonder how they do that? It's actually really easy. You just wash the crust that you want to be pretzel-y with a solution of sodium bicarbonate, just baking soda. It's a little bit basic. It accelerates the Maillard reaction. That crust gets browner and thicker and different tasting than just when you let the reaction happen on its own without base. Okay, so cooking class, Star Wars class, not HA1C lab interpretation class. All right, with that, we got a ton more to do with carbohydrate structure, but let's take a break and we'll pick it back up in about 5 minutes.